Hello everyone, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. This time we're getting into the corpses of stars and what happens after everything has died and gone in a star. That star has really evolved and it's shed its outer layers and maybe formed a planetary nebula, and so what's left behind? And we're going to begin with a low mass star remnant, meaning white dwarfs. What happens to these cores of the dead stars? They continue to collapse until either there's some new pressure that takes hold and prevents this collapse, and then they settle into a new state of equilibrium. And if they're too massive, then they will collapse to zero radius and become a black hole. And everything in between, those are the remnants of stellar evolution. So we really have to think about the nature of dead stars using up all their fuel and the fact that they raise pressure to match the gravitational pull. And their final fate depends mostly on the remaining mass of the core. Lower mass stars become white dwarfs, and they're supported by something we'll discuss shortly, which is called electron degeneracy pressure. The more massive stars collapse down to neutron stars or black holes, and so therefore the remnants are the fossil records of stellar mass evolution and their internal physics. After a star has shed its planetary nebula, all that's left behind is a white dwarf. A white dwarf is composed principally of carbon and oxygen, and it's held up by electron degeneracy pressure. And a typical white dwarf is about the size of the Earth, and the more massive one is, and the smaller it is. And this is because white dwarfs are supported by degenerate matter, and specifically degenerate electrons. These electrons are moving very fast, but the nature of degenerate laws of physics prevent them from actually losing any energy. But the atomic nuclei from which they've been freed aren't degenerate, so they can lose the energy. White dwarfs therefore shine as nuclei lose the energy, and they radiate that light away into space. And no other energy is generated. There's no fusion happening. It's not compressing to make gravitational energy as in the Kelvin-Helmholtz mechanism. Thus, white dwarfs are actually what we would call retired stars, and they're spending their life savings. Eventually, after about 10 trillion years, the nuclei cool down and the luminosity would drop, and we're left with what's called a black dwarf, a cool white dwarf which no longer radiates any energy. Once again, white dwarfs are compact, exposed cores after ordinary fusion has ended, and this HR diagram gives a cue. The hot stars are on the upper left, where high luminosity is going to the top, and white dwarfs land at the lower left, but they're faint. So the faintness comes from the fact they have a tiny surface area, and not the fact they have a cool surface. And we see the path, the trajectory there is a sun-like path. First it starts with the main sequence, and then it goes to the giant phase, and then it goes to the planetary nebula phase, and then eventually all that's left is the compact core. Now we're going to go into a bit of a history of the nature of the discovery and understanding of white dwarfs. The first white dwarf discovered was the triple star system of 40 Eridani, which contains the relatively bright main sequence star named A in the system. 40 Eridani is a magnitude 4 star that's about 5 parsecs away. And here we see it's in the southern December sky around 10 p.m. And the inset shows the colors and relative brightnesses of the 3-star system. As we can see, 40 Eridani A is orbited by the closer binary system of the white dwarf 40 Eridani B and a main sequence red dwarf 40 Eridani C. And with about an 8,000 year period and a distance between A and the BC pair of about 400 astronomical units. The pair on the right is separated by only about 35 astronomical units, and their orbital period is about 230 years. It's always interesting to see these pictures translated into the distances, and we do that through the magic of astrometry and watching their orbits over time, which we'll see shortly. The big thing to note is that 40 Eridani B is distinctly blue compared to the other two stars. And amazingly, this faint pair was first seen by William Herschel, who discovered the pair 40 Eridani B and C, in January 31st of 1783. In 1910, a long time later, Henry Norris Russell, Edward Charles Pickering, and Wilhelmina Fleming discovered also that, despite being a dim star, 40 Eridani B was spectral type A, or white. This star was far out of the normal pattern of the growing list of Russell's color magnitude diagrams that he was creating back in the 1910s. At the time, though, Russell publicly suggested that the spectral type could not possibly be correct. But the spectral type of 4-day Eridani B was independently confirmed in 1914 by Walter Adams. Around the same time, in 1917, while investigating a large proper motion star, Dutch-American astronomer Adrian van Maanen discovered this star very close to his intended target, and it had a bigger proper motion than the one he was investigating, so it was a serendipitous discovery. Here we see the faint star's location in Pisces, late at night about 10 p.m. in the southern October sky. Van Maanen estimated that the annual proper motion as 3 arc seconds, and poking around, he found that this star had been captured on a plate in 1896 in November for the Cartes du Ciel catalog of Toulouse, and it showed an apparent magnitude of 12.3. He then took spectroscopy of this faint, high proper motion star and found prominent absorption features of the calcium K line and H beta. These spectral features led van Maanen to assign it a spectral classification of F0, and it was initially known as van Maanen's F star. A year later, in 1918, American astronomer Frederick Sears obtained a refined visual magnitude of 12.34. 2 years later, van Maanen measured and published a parallax estimate of about 2.46 arcseconds. And that led to a distance of about 4.3 parsecs, giving it an absolute magnitude of 14.8. So therefore, this became the faintest F-type star known at the time. And in 1923, Dutch-American astronomer William Leuten published a study of stars with large proper motions in which he identified what he called van Maanen's star as one of only 3 known white dwarfs, a term he coined. And these are the stars that have unusually low absolute magnitude for their spectral class, lying well below the main sequence on the HR diagram of stellar temperature versus luminosity. Next, we see the subject of the current lecture, Sirius, with its faint companion, Sirius B, at midnight in the southern winter sky. These 3 white dwarfs, the first discovered, are the so-called classical white dwarfs, and this was the sum total of the known white dwarfs in 1922. By 1939, the total known and discovered count rose to 18, and Leuten and others continued to search for white dwarfs until the 1940s. By 1950, over 100 were known, and by 1999, 2,000 were known. And since then, the Sloan Digital Sky Survey has found over 9,000 white dwarfs. Finally, ESA's Gaia mission has, by its data release 3 in 2022, added about 360,000 candidate white dwarfs to the pool. So now, let's take a closer look at the discovery and properties of Sirius B. We begin our real study of white dwarfs with Sirius, the brightest star in the night sky and a familiar landmark in Canis Major. Its visual brilliance makes it a really easy target for early observers, but that same brightness makes the discovery of its faint companion quite difficult, and therefore we start with naked eye astronomy and then move to precision measurement. In 1717, Sir Edmund Halley discovered the proper motion of stars. Proper motion is the slow angular drift of nearby stars across the sky relative to background stars. And this was incredibly groundbreaking because it had been presumed to be fixed in their positions throughout history. Halley compared his contemporary astrometric measurements with those from the 2nd century AD given by Ptolemy's Almagest. He noticed that there were bright stars, such as Aldebaran, Arcturus, and Sirius, had moved significantly, with Sirius having progressed about 30 arc minutes or half a degree, the diameter of the moon, to the southwest. Sirius was one of the most important examples of this proper motion effect. This Palomar Sky Survey photograph of Sirius highlights the interesting observational problem. Sirius is so bright that it overwhelms the surrounding field and that any faint nearby companion would be easily lost in the glare. A white dwarf companion would not be found by simply looking at a pretty star field. It required astrometry, careful measurement of the star's changing position, which was, of course, not possible for Edmund Halley back in 1717. In 1836, the German astronomer Friedrich Bessel discovered the parallax of a different star, 61 Cygni. Concurrent with his work on 61 Cygni, he observed Sirius for 10 years, but was ultimately unable to detect a parallax. Scottish astronomer Thomas Henderson used his observations made in 1832 to 1833 and South African astronomer Thomas Maclear's observations in 1836 and 7 to jointly publish in 1839 the first well-established parallax of Sirius, 0.23 arcseconds. Astronomers adopted a value of 0.25 arcseconds for much of the 19th century. It is today known to have a parallax of nearly 0.379 arcseconds, which corresponds to a distance of 2.64 parsecs, or 8.61 light years. Back in Germany in the 1830s, Friedrich Bessel, undaunted, he continued to observe Sirius's proper motion, and by 1844 he had deduced from these observations that it had an unseen companion orbiting it with an orbital period of about 50 years. Bessel passed away in 1846, never having seen the companion, but knowing it was there. About 16 years later, in 1862, American telescope maker and astronomer Alvin Graham Clark first observed the faint companion while testing a large refractor. It's now called Sirius B, or affectionately the pup. And no one knows where this lovely little nickname came from for the tiny companion to the dog star, but there it is. We have it called the pup, but it has no provenance or really knows where that nickname comes from. Clark's 1862 observations confirmed Bessel's earlier prediction of a hidden companion, and it was exactly where Bessel had predicted it to be. Sirius A and B both orbit a shared center of mass, and their apparent orbit can be mapped easily over decades because the system is quite nearby. Neither star is, of course, fixed at the center. Both move around this common center of mass, and the proper motion through space that was observed is actually a braided path as a result. Because now an orbit can be defined, the system of Sirius A and B is now a laboratory, because now we can combine this with long-term measurement to learn the masses of Sirius A and Sirius B. The pup was seen to be about 1,000 times dimmer than Sirius. However, by watching the proper motion, Clark reported that the masses of the two were about 2.3 and 1 solar mass. To derive their masses, the mean distance between the two stars had to be determined. With a good parallax distance and good astrometric data, we can use Newton's form of Kepler's law to determine the sum of the masses. This can be decomposed into individual masses if we can determine the distances from the center of mass. This is possible because of the close proximity of Sirius. By 1915, the mass of Sirius B was known to be about solar mass, and this caused a lot of consternation in the astronomical community. What we're looking at here is a compilation of data of 150 years of observations from 1862 to 2016, made by Bond et al., published in 2017. And this tracks the position of Sirius B as it orbits Sirius A. It combines a lot of early visual measurements, starting with the discovery in 1862, some photographic plates, and the high-precision Hubble Space Telescope astrometry to map the full apparent orbit on the sky. And this result gives us a very precise orbital solution. The system has a period of about 50.13 years, and the orbit is highly elliptical, and the long time baseline allows an extremely accurate determination of the star's masses and orbital geometry. Conceptually, this plot shows the apparent ellipse of Sirius B around Sirius A, with older measurements scattered and modern HST points tightly constrained, illustrating how the observational precision improved over time. And this is one of the best examples in astronomy of how long-term, century-long astronomy and modern space astronomy combine together to give a precise stellar mass and orbital physics. This orbit that's mapped is therefore a long time series dataset and not a single snapshot. It's just important to note that they are still orbiting a center of mass, but what we've done is reduced the data such that we pretend that Sirius A is fixed in its place in the sky to make this graph. Now we get to a very interesting set of information. Sirius A is known to be one of the closest stars. It's also the brightest star in the sky, and having a known companion that was very dim but seemingly massive was a source of great curiosity. When the next apastron happened 50 years later, in 1915, Walter Sidney Adams at Mount Wilson Observatory observed the spectrum of Sirius B, and it was determined that it was a faint white star. With a distance and apparent magnitude, the absolute luminosity could be found. Combining the known luminosity and the spectroscopically determined temperature gave a radius of about 0.008 solar radii. This was a huge surprise. So what Adams did was measure Sirius B's spectrum, and he found that it was hot, really hot, around 25,000 Kelvin. So a hot surface radiates strongly per square meter. Sirius B is very faint, despite being so hot, so the emitting area must be tiny. The Stefan-Boltzmann law links luminosity, radius, and temperature. If the temperature and luminosity are known, the radius can be inferred. A radius of 0.008 solar radii is roughly the size of the Earth. This is the white dwarf shock, nearly a solar mass compressed into a planet-size scale. Let's look at how he did this. We have two equations, the link between the luminosity, the distance, the flux, and the luminosity, the size, and the temperature. The equation on the right is the Stefan-Boltzmann law, and the equation on the left is how a bright source is apparently dimmer with distance. On the left-hand side, the d is not the diameter of the star, but rather the distance to the star, and b is the flux, or brightness, and L in both cases is the luminosity, the total luminosity energy per second. On the right equation, the Stefan-Boltzmann law, the r here is the radius of the star, and sigma is the Stefan-Boltzmann constant, and T is the temperature to the fourth power. The first thing we'll do is we'll compare them. We're going to compare some star, which has a subscript star, to the sun, which is the circle dot. So we're going to make a pair of ratios. The first ratio on the left is the luminosity of a star compared to luminosity of the sun, and we just basically set them to be something, some stellar, some star's property, some distance, and some brightness or flux compared to the sun. And on the right-hand side, we do exactly the same thing. Notice the luminosity of the star and the luminosity of the sun are the same. That ratio is the same in both equations. So we equate them, and this allows us to get an interesting set of relationships. For these two ratios, the luminosity of some star compared to the sun is the same in both ratio equations. So we set them equal to each other. Now I want to take a little step back, and where's that 4 pi come from? So the 4 pi d squared on the left is all the light from that source being spread out over a sphere of radius d. And on the right-hand side, the 4 pi r squared is the size of a sphere. That is the surface area of a sphere that is emitting all of the light. So the sigma t to the fourth says how much energy is being emitted per unit area. And the total area is 4 pi r squared. We end with equating the two ratios, and we're going to start solving for these things. Let's first understand how we measure brightness. In 1856, Norman Pogson at Oxford University proposed the still used modern system of magnitudes, defining them as follows. 5 steps in magnitude is, by definition, a factor of 100 in brightness, and the greater the magnitude, the fainter the star, and the standard of brightness is the star Vega, which is defined to have 0 magnitude in every filter. So what we're going to do here is we're going to rewrite this thing in terms of the magnitude system. We want to solve for the radius. So we've grouped the flux over on the right-hand side and translating that ratio of flux or ratio of brightnesses into magnitudes. And then we take the square root of both sides and we're left with what we see on the bottom. Now that we have all that set up, we can plug in known constants. The solar radius is about 7 times 10 to the 8th meters. The solar temperature is 5,772 Kelvin. The distance to the sun in meters is about 1.5 times 10 to the 11th meters. And the visual magnitude of the sun is negative 26.74. We plug all that stuff in and solve for the numbers and convert meters to parsecs, because we don't measure meters to a distant star. We measure things in parsecs. So we now have the radius of the star is equal to about 2.15 times 10 to the 16th in terms of meters, where the distance d to the star is in parsecs and the temperature is in kelvins and the magnitude is a unitless in value. Now we can estimate the radius of Sirius B from known data. Sirius B's temperature is 25,000 Kelvin, and Sirius B's distance is 2.639 parsecs, and Sirius B's visual magnitude is 8.44. You plug all that in, and you get a radius of about 1,850 kilometers. Well, the problem is that today's known Sirius B radius is about almost 6,000 kilometers, or 5,600 kilometers. And the Earth's equatorial radius is about 6,300, for comparison, 6,400 kilometers. This estimate that we just did is really, really wrong. So we have some little crazy happy accident that we don't understand. So let's figure out where this estimate and why people think it's the size of the Earth and not much smaller. In order to correct this, we have to know how to translate what we know as visual magnitude into what we call bolometric magnitude. Bolometric magnitude would be the magnitude of the star if we did not have any filters and could collect all of the light. But we can't do that. We have to practically use a filter, and the filter is the V filter, or visual magnitude filter. And so it would be brighter if it could collect all of the light that we see, but we're only looking at a very small window on it. So we have to apply a correction. And this is called the bolometric magnitude correction. And the estimate for that from both either Flower or Ecker et al. In 2020, the bolometric magnitude should be the visual magnitude plus some correction. And the estimate is that the bolometric correction is about minus 0.25. Therefore, the bolometric magnitude is what we really want, is 6.0. This bolometric correction comes about because the Stefan-Boltzmann law says energy radiated all wavelengths, but we only measure in the visual magnitude. So we have to translate between the two. That's where this bolometric correction comes from. With the bolometric correction of minus 0.25, now we get an updated Sirius estimate for about 5,700 kilometers, but we know more precisely that Sirius is about 5,634 kilometers, and of course the Earth is about 6,380 kilometers. That's a much better estimate. Once we actually know the size of Sirius B, we can then determine something really fascinating. Astrometrically, we know the mass of the white dwarf, and now because of the combination of Stefan-Boltzmann law and the brightness, we know the size, so that we can determine the density. And this is really interesting. If we take the mass of the pup and then we divide it by the volume of the pup, which is 4/3 pi r cubed, we get the average density of about 3 times 10 to the 9th kilograms per cubic meter. Now, since it's a sphere, we can then calculate g, or the gravitational acceleration at the surface of the pup, and that is 4.6 times 10 to the 6th meters per second squared. If we compare that to the Earth is 9.8 meters per second squared. So the gravitational acceleration is 1,000,000 times that of the Earth, which means that if you dropped just a hammer, if you take your average little hammer that you buy at the hardware store, weighing about 2 kilograms, and you dropped it from 1 meter off the surface of a white dwarf, in that 1 meter, it would accelerate to 2.9, or about 3 kilometers per second, or 6,500 miles per hour inside of 1 meter. And it's pretty fast. That's really fast. And it would strike the surface with 2 kilograms of TNT, which would be a pretty loud bang. Because of this very strong gravitational pull that a white dwarf has from the surface, the light that leaves it has to rise out of a very powerful gravitational field. And therefore, according to the theory of relativity and general relativity, there must be a gravitational redshift. In 1959, the Pound-Rebka-Snyder experiment showed that this actually does happen. The frequency of a photon measured at the top of a tall tower is different than the frequency that it was emitted from. But this experiment is more like a special relativistic experiment. What we need to use is the geodesic of a freely falling photon inside of a gravitational field. And to do that, we need the Schwarzschild metric, and we need to measure the path that it takes. The Schwarzschild metric shows how the space-time is bent, as opposed to saying it's simply rising out of a classical Newtonian gravitational field. We now link the nature of space and time together and get the same result using general relativity. This gravitational redshift has been measured. Joyce, Barstow, Harlan, Bond, Kaiswell, and Burley back in 2018 published their observation of Sirius B's spectra taken by the Hubble Space Telescope. And you can see the spectrum here, that it has a distinctly different shape. And it's the width and character of this particular spectral shape with the dip of the absorption feature at H alpha, which is a hydrogen absorption feature, looks very different than a star that is, like a different kind of star, a not so compact star. It is the width and profile of this line that actually helps you determine the gravitational redshift. By studying that spectrum, they were able to determine the gravitational redshift. We do know that the laboratory wavelength is 6562.81 angstroms, but what they observed it to be at was 6566.47 angstroms. That small 4 angstrom wavelength shift, combined with the known radius of Sirius B of 0.0084 solar radii and a redshift of about 81 kilometers per second, gives a mass of 1.017 solar masses. Again, a 150-pound person would weigh 50 million pounds standing on the surface of Sirius B. This is an incredibly weird environment. Finally, with all this information, we can get the vital stats for Sirius B. The mass is now known to be 1.02 solar masses, or about 2 times 10 to the 30th kilograms. Its radius is just under 1% of that of the sun. The luminosity is about 5% of that of the sun. The surface temperature is over 25,000 Kelvin. The average density is just under 3 billion kilograms per cubic meter. The escape speed is about 7,000 kilometers per second, or about 2% the speed of light. By studying the star more closely and understanding its origins and its spectra, we can determine roughly that its age is about 228 million years, and the progenitor star mass is about 5 solar masses, and the progenitor star type is about a type B. Here we see a visual comparison of what the size of the white dwarf would be next to the Earth, and if this were really true, the Earth would be scorched to a cinder if the white dwarf was right next to it. Also, it would be shredded because that's a solar mass right next to the Earth, and this would be a very bad day on Earth if this diagram were true. These stars are incredibly odd on the HR diagram. Hertzsprung and Russell were making a very large study back in the 1910s about all these stars, and they found that they lived in the lower left-hand corner of the HR diagram. Most of the stars of white dwarfs are roughly around between 10,000 and 30,000 Kelvin, but many of them have also been observed to be hundreds of thousands of Kelvin in temperature. The most complete data set of all known white dwarfs comes from European Space Agency's Gaia mission, and we see here one of their more recent data releases, and most importantly, the white dwarf main sequence. Here we see 25,000 white dwarfs represented in a color magnitude diagram taken by the European Space Agency's Gaia mission. It's interesting that you can see a split in the middle of this white dwarf main sequence, and it has real ramifications for the ages of white dwarfs and how they cool off and how they emit their light. Well, I'll leave you with this picture of an artist's impression of how the binary star system Sirius A and its blue companion Sirius B might appear to an interstellar visitor coming by. Sirius A dominates this wonderful little scene, and Sirius B is the small but very hot and blue-white star on the right. Again, they go around each other every 50 years, and because of their orbit, we've learned their masses. And by looking at their spectrum, we can learn the temperature. And by learning their distance, we can determine from their temperature and their distance the size of the thing. Because we know the size of the thing, and we can see it astrometrically, the mass, as well as getting the mass from just the spectra itself using the gravitational redshift, we can combine these two things together and learn the density of a white dwarf. and find that these are incredibly dense, strange stars. And it is these strange stars that we'll talk about far more extensively next time.